Hello, in this lecture we're going to take a very general look at the regulation of consciousness, and we're going to focus on two important structures in the central nervous system, that being the cerebral cortex and the reticular formation in the brainstem. So we're going to make some definitions initially, then we're going to have a little look at the reticular formation and its various components. We're going to think about how you can assess cortical function and the level of arousal, and this is using a couple of different tools, one being primarily a clinical tool, the Glasgow Coma Scale, and one being the EEG. Then we're going to look at sleep, particularly its stages, some of the mechanisms of sleep, and some of the disorders of sleep, and we're going to finish by looking at disordered consciousness. So let's start off by trying to define what we mean by consciousness. And in fact, consciousness is a very difficult concept to define unambiguously. And philosophers, neuroscientists have been debating what consciousness is for hundreds of years. The first distinction, though, that we should try to make is that between arousal and consciousness itself. Now, the term arousal refers to an emotional state, and this emotional state is associated with some kind of goal or the avoidance of something noxious. So if you consider the little dog at the bottom of this image here, that dog is very definitely demonstrating a state of arousal. It's looking at something, its ears are up, and maybe it's looking at that scary looking zombie stood next to it. So arousal is about being involved with some kind of goal or avoiding something. Whereas consciousness is much more difficult to define. But we all know kind of what consciousness means for us, and that it must have something to do with some kind of awareness, and that being the awareness of the external world, so we can perceive the external world, and furthermore, we're capable of perceiving our own internal states as well. The idea of exteroreception relating to the outside world and interoreception relating to the inside world. So that's consciousness very, very broadly speaking, and I'm not going to try to define it any more than that. However, I've included these images at the bottom just to make you think really, and for us to have a little bit of fun for a minute or so. So I mentioned this zombie here. Now, when you speak to philosophers about consciousness, they may sometimes invoke the idea of the philosopher's zombie. And the philosopher's zombie is in fact nothing to do with humans who have been affected by a virus and then go around eating people's brains. The philosopher's zombie is in fact a person who behaves as if they are conscious, but in fact has no internal feelings at all. He does not have any awareness, any subjective awareness. And you can debate about whether that is even possible in principle, but that is the philosopher's zombie, which is an interesting thought experiment. The next character that we have here, moving from left to right, is the great Alan Turing. Now, Alan Turing, as you should be aware, made many, many important contributions to both mathematics as well as biology, as well as being the father of artificial intelligence and modern-day computing. And one interesting idea that Alan Turing had, and was actually able to prove mathematically, was that you should be able to run a computation on any kind of hardware. Okay, so for example, the computation that's present within your iPad should in principle be able to be run on a PC, so you could emulate it on a PC. But Turing went even further and said, well, you could maybe even run that software on a system which is mechanical, for example, using ball bearings falling under gravity or something like that. So Turing argued for this idea of substrate independence. And I'm talking to you about this just for your own interest, to try to stimulate your fascination in this idea of consciousness. Because could it be possible that if the brain works as a computer, and we don't know that for certain yet, but it's a reasonable assumption that the brain works like a computer. If the brain works like a computer, then maybe it's software, so to speak. The internal states could actually be simulated on a conventional computer. Maybe one day we could upload a mind into a computer and it might be conscious. Finally, on the bottom right hand side we have an image here of an android called Mia from the Channel 4 series Humans. She, of course, was a synthetic life form which developed consciousness. So, I find it interesting to think about this, and this is very much an aside for your own entertainment if you get a chance to read about consciousness in a bit more depth. So let's move on. In order for us to be conscious, and here I'm talking about consciousness in the simplest possible way, that is, we're awake essentially. In order for us to be conscious, we need two fundamental ingredients. The first thing we need is a cerebral cortex. Okay, so we need the cerebral cortex. And the second thing we need is the reticular formation. Now, the reticular formation is a diffuse set of neurons sitting throughout the full length of the midbrain. And it's characterized by having many inputs from the sensory system, but also inputs from the cerebral cortex. Furthermore, the reticular formation also projects back up to the cortex, and these are excitatory. So if we take a look at the image on the right hand side, the red neurons here are the pyramidal neurons of the cerebral cortex, which are projecting downwards to, as you know, lower motor neurons, for example, but furthermore projecting to the reticular formation itself. But the reticular formation sends inputs back up, and we can think of these as being this green neuron here, monoaminergic projections and others going back up to the cortex itself. So we have a positive feedback loop in play here, whereby the cortex and the reticular formation mutually excite each other. And that is very important because that is what is helping to keep us awake right now. And just as an aside, whenever we see a positive feedback loop in nature, this tells us that there is a binary decision being made, essentially. There is a system which can be in one of two states. So we've said that we have a positive feedback loop maintaining consciousness, so you are either conscious or you're unconscious. Remember other positive feedback loops. So during childbirth, parturition, we have a positive feedback loop involving oxytocin. So you're either giving birth or you are not giving birth. And you know of a number of other positive feedback loops whereby we are able to regulate the body in either one of two states. So positive feedback loops are absolutely fascinating and vital for our normal functioning. So a little bit more detail on the reticular formation. As we said, it is a population of specialised interneurons present within the brainstem and throughout the full length of the brainstem, so there is reticular formation in the midbrain, the pons and the medulla. It has many inputs. It has inputs from the sensory system and inputs from the cortex as well. Okay, and you can kind of relate that to your everyday experience. Think about trying to get to sleep. You can't get to sleep if you've got a lot of sensory input, because it is stimulating the reticular formation. Furthermore, you can't get to sleep if you've got a lot of thoughts in your head, so that's a lot of input from the cortex down onto the reticular formation. The outputs from the reticular formation are widespread. They are to the thalamus, and that can help to stimulate the cortex, and as you should recall, if you want to get to the cortex you do have to go through the thalamus. Furthermore, the reticular formation can regulate the amount of information flowing through the thalamus, and that's important in going to sleep. The reticular formation projects to the hypothalamus, which in turn projects to the cortex. It projects to the basal forebrain nuclei, and it also projects to the spinal cord. And in fact, these spinal cord projections of the reticular formation are particularly interesting because these are involved in the regulation of muscle tone. And we know that in one stage of sleep, rapid eye movement sleep, the muscles are effectively paralysed by strong inhibition, which is descending down from the reticular formation. Now, a lot of the reticular formation is devoted to arousal, and keeping us awake, and that is known as the reticular activating system. And the reticular activating system is composed largely of neurons that send projections up to the cortex to keep the cortex at a high level of activity. Now, how do you go about assessing consciousness? So, we've said it's difficult to define, and that is true, but we have a number of tools whereby we can assess the level of consciousness in patients or research subjects for that matter. And the classic one that you need to be aware of is the Glasgow Coma Scale, and I include this slide primarily for your reference. And I have made a separate video talking about the rationale for why the Glasgow Coma Scale is set up in this way. But essentially, the GCS looks at 3 domains of neural function. It looks at eye opening, it looks at the best motor response and the best verbal response. And it should be emphasised that we're always thinking about the best response that the patient demonstrates. So the best response possible with regard to eye opening is that the patient is spontaneously opening their eyes, looking around. Whereas the worst response is they don't open their eyes even to a painful stimulus. Regarding the motor system, the best possible response is that they obey verbal commands, whilst the worst possible response is that they are demonstrating this extensor posture. Okay, and this extensor posturing here suggests that there is very serious damage quite high up along the central nervous system. Relating to verbal responses, the best verbal response is that they are oriented to time and place, whilst the worst is that they don't make any response at all. And as I alluded to just now, the worse scores in the GCS tend to relate to higher levels of damage in the central nervous system. But I've made another video just to emphasise that even more. So the GCS is probably one of the most common tools used to assess consciousness in patients across the world. Now, there are other methods to assess consciousness, and another method to assess consciousness is the electroencephalogram, or EEG. And I'm not interested in you knowing great detail about the EEG. Just realise that what you are doing with the EEG is putting a whole bunch of electrodes all over the scalp of the subject or patient. And each one of these electrodes is capable of measuring the electrical activity in the brain in that region. And the kind of tracing that you get looks like this on the right hand side. And depending on what you get the patient to do, you can get different tracings. Now, the EEG is an excellent way of assessing consciousness, and it is used, for example, clinically in the intensive care setting. It has very, very good temporal resolution, so it's able to see electrical changes in the brain on a millisecond timescale. However, it has a very, very poor spatial resolution, so in terms of using EEG to localise lesions, it's not all that good. Because it's looking at the summed activity of thousands of neurons, in fact probably more like hundreds of thousands of neurons in a given part of the cortex. And we're going to look at the EEG in a little bit more detail later on when we consider the stages of sleep. But that's all I want you to know about the EEG. Now, the central nervous system has some very interesting properties, and these properties have been determined by studying the brain using things like EEG. And one interesting property that the central nervous system seems to have is that it has a tendency for the neurons to become synchronous. And the best analogy I can think for this synchronicity that we see in our everyday lives is if ever you've been at a theatre performance or a football match and applause starts, you might have noticed sometimes that the applause can all become synchronous, so everyone is clapping simultaneously. And I like to think of that crowd as being an excellent analogy for neurons in the brain, because the neurons in the brain, as you know, are connected to one another. So let's see if we can demonstrate this a bit more interestingly using these metronomes. So if we watch these metronomes, you'll see something very interesting. First of all, what the guy is going to do is he's going to run the metronomes all independently. So they're all connected to this wooden this wooden plank here, and they're all running independently. They're not coupled to each other in any way. But then what the guy does is he puts the plank on top of a couple of Coke cans, and then information is able to travel from one metronome to its neighbour. And then you'll note that they all become synchronised. So let's see if this works. So here we have the metronomes all running independently. They're not coupled to each other in any way. And think of them like neurons, but without connections. And by putting them on the cans, you're connecting these neurons to one another. And they're able then to share information, to communicate. And you get to this wonderful situation where all 5 of the metronomes are ticking precisely at the same time. So I think that's a really neat demonstration of how synchronicity is almost a fundamental property of any system where there are oscillators coupled to each other. And one of the best examples of that, of course, is the brain. So what's that demonstration got to do with consciousness and sleep? Well, what we know is that during sleep, the neurons of the brain go into a synchronous pattern of firing. And so it does seem to be that if the brain is deprived of its sensory input, then synchronicity sets in. And we'll see how that synchronicity sets in when we look at the EEG tracings of the various stages of sleep. Let's start off, though, by looking on the left-hand side at this graph, which is called a hypnogram. So a hypnogram is a graph of sleep stages, and this can be derived in a sleep lab, which is present in many hospitals around the country. Sleep has a number of stages. Obviously up here we've got the awake subject, and then on the hypnogram it is represented by successively deeper stages, going down to stage 1, stage 2, stage 3 and stage 4. And stage 4 sleep is the deepest stage of non-REM sleep. And you note that when you get down to stage 4, you stay in stage 4 for a while, and then we see that during the night we then rapidly come out of stage 4 and go into rapid eye movement sleep. And in rapid eye movement sleep we see a distinctive EEG pattern, and we also see movement of the eyes themselves, hence the name. And this cycle of going down through the stages of non-REM sleep and then back up to REM sleep, the cycle, we go through about 6 cycles per night. Okay, so that's the typical hypnogram. Now let's take a look at the EEG changes which are measured during the night. So if you put a set of electrodes on a patient's scalp, get them to go to sleep and then measure their EEG, you will get something like this. And it always amazes me how people can go to sleep so easily wired up to these things, because it seems really quite uncomfortable. So let's start off right at the top. And this is a typical EEG pattern that we would see in a subject that is awake. And it is characterised by fairly low amplitude activity, and the frequency is quite random. Okay? Now this random pattern is very typical of activity in the brain when the brain is doing something. Okay? The brain is working away at information, processing information. And it's random because, of course, sensory information is coming in randomly. There is no necessary order to it, and so that imparts a randomness to the EEG whilst you are awake. If you close your eyes, then what happens is 2 things. First of all, the EEG pattern becomes slightly more ordered. You can see it does look a little bit more ordered than it did in the awake state. And secondly, the amplitude has increased a little. Okay? And what's happening here, when you close your eyes, you deprive the brain of a major source of sensory input. Remember that us humans are largely visual animals, and so therefore closing your eyes takes away a large amount of sensory input from your brain. And what that does is it allows the neurons to start manifesting their tendency towards synchrony. So this more ordered pattern is actually, we're starting to see neurons going into a little bit of synchrony. And as neurons go into synchrony, the amplitude can increase because they're all firing simultaneously. So we closed our eyes. Then we start to go down into stage 1 sleep. And in stage 1 sleep, what we start to see is a background looking a little bit like the state where the eyes are closed. But then we start to see these theta waves, okay? These theta waves here, and they're starting to appear. And this is a pattern that we see throughout the stages of sleep, in that these waves will appear, and then in the next stage there's a background of these waves superimposed upon by a new set of waves. So in stage 1 we'd see a background of this relatively random activity, but now even more synchronous and slow theta waves are coming into view. And the theta waves are running at about 5 Hertz. So with eyes closed we were running at about 10 Hertz, whilst in stage 1 sleep we've slowed down to about 5 Hertz. Stages 2 and 3 can be combined for our purposes. And in stages 2 and 3 we see a background of theta activity, but superimposed on that are two new waveforms, the so-called sleep spindle and the so-called K complex. Now there's a lot of detailed neurophysiology behind the sleep spindle and the K complex, but from a simplistic point of view I think of the sleep spindle as essentially spikes of activity arising from the thalamus. So as we go down through these stages, the thalamus is becoming progressively more and more inhibited. But sometimes the thalamus kind of jerks awake and sends a spike of activity up to the cortex, and I think that's what the sleep spindle is. Whilst the K complex, these very large, high amplitude but very slow waves, are actually a prelude to what we will see in the deepest or stage 4 of sleep, where we have this slow synchronous activity. So the K complex is a prelude, if you like, to the delta waves that we see in stage 4. And when we get to stage 4, we have very slow frequency activity, only about 1 Hertz, and you can see it's very high amplitude, and these are known as delta waves. And this is, slow wave sleep, stage 4 sleep, delta sleep. And these you can see are representing a huge amount of synchrony within the cortical neurons. And that represents, if you like, the intrinsic rhythm of the cerebral cortex, because in stage 4 the thalamus has largely been inactivated and the cortex is being allowed to get on with what it needs to do during sleep. Now, as we said when we studied the hypnogram, we do go from stage 4 up to REM sleep very rapidly, about 5 or 6 times per night. And the interesting thing to note when you look at the EEG trace for REM sleep at the bottom here is that REM sleep looks, for all intents and purposes, identical to the EEG when we are awake. So REM sleep looks identical to the awake EEG. And it should come as no surprise that REM sleep is the stage of sleep when we do dream. We dream also in slow wave sleep, but REM sleep is most prominently associated with dreams. And so it seems that in REM sleep the cortex is doing something interesting. It's maybe replaying events from the day, for example, and this manifests as a brainwave activity that looks very much like what the brain looks like during waking. So by looking at the waveforms on the EEG, you can assess which stage of sleep the patient is in, and that is how the hypnogram is derived. Now, what's the neural mechanism of sleep? Well, it's very, very complex and still relatively poorly understood. We're going to particularly focus on slow wave sleep, that is non-REM sleep in this slide. But basically, as we said before, sleep is about deactivating the reticular activating system and hence, of course, deactivating the cortex, and this involves inhibition of the thalamus. You need to put the brakes on the thalamus during sleep because you don't want that sensory information to get up to the higher levels of the cortex. And we know that the positive feedback loop between the reticular activating system and the cortex is inhibited, and we know that this leads to decreased cortical activity. And we can inhibit this positive feedback loop in a number of ways, but primarily by removing sensory inputs. So think about what you do at night in your bedtime routine and how this will impinge upon the positive feedback loop. So for example, you close your eyes, obviously, things are quiet, you're not too hot, you're not too cold, and you try to clear your mind of any thoughts. So this is the way that you take out the input from the positive feedback loop and gradually go off to sleep. Now, REM sleep is slightly different, and another name for REM sleep is paradoxical sleep. Now, REM sleep is not a passive action. It is actually mediated actively by a groups of neurons in the pons. And as we said, EEG activity is similar to that seen during an awake patient, but during REM sleep, the patient is difficult to rouse, difficult to wake up, and this is due to strong inhibition of the thalamus. The thalamus is really being strongly switched off during REM sleep. Furthermore, muscle tone in most of the body is lost, and this is down to the inhibition of lower motor neurons by glycinergic fibres, which are running from the reticular formation down to the spinal cord. And it's believed that this is present in order to stop us from acting out our dreams. And one disorder of this is, for example, somnambulism, sleepwalking, where patients can get up and walk around. And in that case, they haven't inhibited their spinal cord as they normally should. However, eye movements and some other cranial nerve functions are preserved during REM sleep. It's called rapid eye movement sleep, isn't it? Also, the function of the trigeminal nerve is preserved, and this can be the cause for so-called nocturnal bruxism, which is grinding of the teeth in sleep. We also see autonomic effects during REM sleep, including penile erection and loss of thermoregulation. And that's an important one, the loss of thermoregulation, because of course this is how people might die from exposure if they go to sleep outside without adequate shelter. Finally, it is known that REM sleep is essential for life, and we know that if we deprive animals of it, they die. However, we don't know why REM sleep is so essential. So sleep is still a very interesting and wide open field for research. Now, what are the functions of sleep? Once again, we don't really know, to be perfectly honest. There's been a lot of speculation over the years, and a lot of woolly ideas have built up. However, it could be to do with energy conservation and bodily repair. You know, we know a good night's sleep can make you feel a lot better in the morning, so maybe that's something to do with it. We know pretty confidently that sleep is crucial for memory consolidation, so the reverberatory loops between the hippocampus and the cerebral cortex are particularly active during sleep. So if you're trying to revise for an exam, get a good night's sleep to help consolidate those memories. It seems that sleep is involved in the clearance of extracellular debris, and there is a system in the brain which acts in the intercellular spaces called the glymphatic system, whereby during sleep these passageways open up and clear a whole load of extracellular debris. And this, it is known that there seems to be an association between poor sleep and dementia, and so maybe something to do with not clearing out amyloid could predispose patients to dementia if they don't get enough sleep. You also sometimes see these ideas of resetting of the central nervous system during sleep. Now, I'm not entirely sure what that means, and I've left it in here just as a caveat for you, to make you think, is the central nervous system like a computer that you can simply reboot? And I would argue that it is not. So, disorders of sleep. Disorders of sleep are very, very common. And if you work in general practice, you will see people with sleep problems on a daily basis. The truth of the matter is, a lot of patients think that they have some kind of primary insomnia, whereas in reality, most frequently, it is a symptom of other problems. And a classic cause of insomnia is anxiety and depression. So if a patient presents to you primarily with the symptom of inability to sleep, you need to make sure you do a thorough assessment of their mental state and try to determine whether they have some underlying depression or anxiety. Narcolepsy is another one that everyone's fascinated by, but which is really, really rare. Narcolepsy is an interesting disorder for you to read about, because it shows us the power of looking at pedigrees and looking at diseases from a molecular point of view, because by studying a family where a large number of its members were affected by narcolepsy, scientists were able to work out that one form of this disorder is caused by a mutation in the gene for a neurotransmitter, a peptide neurotransmitter called orexin, otherwise known as hypocretin. And what this transmitter does is helps to couple the perception of light to the hypothalamus. So in these patients, they were reporting lower levels of light, I think, to the hypothalamus than were present in reality, and this was contributing to their tendency to spontaneously and uncontrollably fall asleep. Narcolepsy, very interesting disorder, but you may well only see 1 or 2 patients with it in your whole career. A much more common disorder of sleep is sleep apnea. And in sleep apnea, the typical patient in sleep apnea is an obese man. And what happens is that during the night, the extra fatty tissue around the neck and the tongue leads to a temporary occlusion of the airway. And this occlusion can occur hundreds of times per night. And when you occlude your airway during sleep, obviously in order to clear that occlusion, you need to wake up. So these poor people feel terrible, feel absolutely dreadful in the morning. They don't feel refreshed. And that is because they have been awoken hundreds of times during the night due to the fact that they could not breathe properly. And a treatment for that, of course, the best treatment is to advise your patient to lose weight, take exercise. But what can be done in the meantime is to use things like positive pressure ventilation to force air into the airways. So sleep apnea is a very important disorder for you to be aware of. Finally, let's take a look at some disorders of consciousness. And I've tried to order these almost in order of severity, although that is a moot point about which is more severe than the other, as we shall soon find out. These are typically defined by the EEG waveform that is present and other clinical features, and you'll encounter a lot of these when you work on the intensive care unit. So let's start off with the most severe disorder of consciousness, which is brainstem death. And in brain death, what we see is widespread damage to the cortex and the brainstem. And remember, right at the start, we said that for consciousness to be present, we need a functioning cortex and a functioning brainstem with its reticular formation. If both of these are severely damaged, what we get is a flat EEG. We get absolutely no activity in the EEG, a complete flat line, and in that case the patient is brainstem dead. The next condition in order of severity is coma, and in coma what we see is once again widespread brainstem and cortical damage, however maybe not quite as severe as in the case of brainstem death. And we see various disordered EEG patterns, so that the neurons are doing something, but they're not really able to synchronize. They're not really communicating with each other all that well. These patients tend to be unarousable and unresponsive to stimuli, to meaningful stimuli at least. And the reason why this has been said, meaningful stimuli, is of course you may still be able to get spinal reflexes. And in these patients, no sleep-wake cycle is detectable. And that is the key thing that differentiates coma from persistent vegetative state. Because in PVS, patients do seem to have a sleep-wake cycle detectable on the EEG. In PVS, they've got cortical damage, and they do have some disordered EEG patterns. It's very much like coma, but you might see some spontaneous eye-opening as well, and sometimes they can even localise to stimuli. So it seems that in PVS they have more of a functioning brainstem, but it is the cortex, or the connections between cortex and brainstem, that have been affected. And of course, in going from brain death through coma and PVS, the prognosis becomes better. Finally, and not necessarily related to the other three conditions, I've included locked-in syndrome. And locked-in syndrome is a fascinating, albeit rare, condition whereby the cortex is essentially disengaged from the rest of the body. And it's typically caused by involvement of the basilar or its pontine branches, for example in a stroke or a subarachnoid hemorrhage. In these patients, eye movements are preserved and they are conscious, but all of their somatic motor functions are lost from the level of the pons down. And the typical patient that you might see with this can move their eyes, is conscious and aware, but is not able to move any other part of their body. And so this is a tremendously cruel condition, which has very, very significant implications. However, these patients can still communicate, of course, they can hear, and they can also communicate through very clever devices which detect eye movements and enable them to produce verbal instructions. So that's all I've got to say on consciousness and the reticular formation. Thanks very much for listening.